Good day. We are continuing our study of the free response questions. This is the 2018 calculus test number 1 for BC. I'm sorry you don't see my face up on the screen this time. There just wasn't any room to put it because I'm going to be filling the screen with my scribbling nonsense. So here we go. We are talking about entering a line for an escalator. And that is modeled by this rate function, which is a piecewise function. There's this equation from 0 to 300, and then after 300, nobody gets in line. We also know that people leave the escalator at a constant rate of 0.7 persons per second. And we know that when this whole thing started, there were 20 people in line. With all that information, let's go. So how many people entered the line during the time interval 0 to 300? Well, since we know the rate at which they enter, the amount that enter is the integral of the rate. And that's simply what you have to calculate. Now, this is a calculator dependent problem, which I know this year we won't be using our calculators. However, the relationships between the rates and the amounts is a very important thing. So there are 270 people that get on the escalator between 0 and 300. All right, question B. It says there are always people in line in those 300 seconds. How many people are in line at the end, at the 300 second mark itself? Well, we got to figure out each piece. How many people enter in 300 seconds? And we know this answer from the previous problem. Subtracting how many people leave, which is a constant rate of 0.7. I suppose you could have written these together. It doesn't really matter. And there are 20 people in the beginning. So the answer to this gives you how many people are in line at 300 seconds. So we know this answer is 270. Now to calculate this, the antiderivative of 0.7 dt is 0.7t. And we are calculating that at from 300 to 0. Okay. Plus 20. All right, so what's 0.7 times 300? 0.7 times 3 is 21. When I plug in 0, we get 0. So 270 minus 210 is 60, and 60 plus 20 is 80. So there'll be 80 people at the end at 300 seconds. So 20 people started, 80 people at the end of that time. All right, question C. After 300 seconds, how long does it take before there are no people in line? Because remember, after 300 seconds, nobody's getting on, but people are still leaving. So I thought of it this way. It's not the only way to think about it, but here's my first thought. I had 80 people that started. I'm taking away the 0.7 dt. I'm taking away the rate at which they're leaving. Now, that starts at 300. We already know it goes up to 300, so now I'm going to start from 300 and move on to some unknown time. And I want that to equal 0. All right, so we just take the antiderivative, which is 0.7t, evaluating it at x and 300. All right, so then we plug in our numbers here. So 0.7x minus 0.7 times 300 equals 0. 80 minus 0.7x plus 210 equals 0. And we do a little solving here. 0.7x. So I add these up, I get 290. So subtract 290 and divide by negative 0.7. And we find that equals 414,286. So it takes 414.286 seconds before everybody is gone. Now, I don't think it's going to be a big deal this year because of the non-calculator part of the test, but in general, we solve till 3 decimal places. So I don't think that situation will occur. But if you're ever going to use a decimal, make it 3 decimal places. All right, question D. What time is the number of people in line a minimum? All right, so here's what I'm going to do. I'm going to call my equation P of X. X would be the time, P is the number of people. Okay. I know the amount of people that are on this escalator are modeled by this from 0 to, we don't know, some time of the rate of people entering, minus, and the same thing, 0 from some time that we don't know of the rate at which people are leaving, plus 20. This is our total number of people. And we've used this formula before. We used it and figured out how many people were on the escalator at 300. Now, if I want a minimum, I take a derivative. So the derivative of the integral, according to the fundamental theorem of calculus, is just r. And the derivative of the integral, according to the fundamental theorem of calculus, is just 0.7. The derivative of 20 is 0. So to find a minimum, I want to know when this equals 0. So I want to know, when does r of x equal 0.7? Now again, this is only something that can be done with a calculator, and you won't have to worry about that for this year. But you would graph that function of r and find out where the intersection points are. Easiest thing to do is graph r and graph 0.7 and just see where they cross. You will find out that those values happen, that the rate equals 0.7 at these two values, 33.013 and 166.575. Now, wants to know when it's a minimum. So we could find out the max, the local max, the local min, but remember, we're talking about absolute. What is the time that people in line is a minimum? It could be the beginning, it could be the end. So let's just check all 4. And the reason it's not going to be a bad thing to check all 4 is that we already know 2 of them. And I think the time-consuming issue of this problem was putting this all in the calculator when you had to. All right, we know at the beginning there were 20. And we know at 300, because we calculated it, there were 270. Now, how do we calculate this amount? Well, we just put it on our calculator. We plug this in to that equation. Okay, and it takes, it's not too bad to do, but you would use your feature on your calculator for integrals. And what you would find out is that this is about 3.8. And this is about 158. So it's very clear that the minimum happens here. So what you would say, that the people in line is a minimum at the time equaling 33.013 seconds. And you could say, because it says, remember, round to the whole number, there are about 4 people. Okay. All right, that's question 2018. So hopefully you're doing okay with these. We will meet on Thursday, which is, according to my clock right now, on my calendar, it is tomorrow. And if you have any questions on this, I will post new questions on Thursday also. So I hope you have a great night, and I'll see you later.